Welcome to video lecture D1. This is an introduction to determinants. I'll be your escort, Tom Roby. Here are the outline and objectives. First, we'll need to memorize the inductive definition of the determinant of a square matrix and compute some examples to get a handle on what this thing looks like. But then we're going to generalize this to what's sometimes called the Laplace expansion. This computes the determinant of A by things called cofactors, which are similar to the definition we're going to use, but allow us greater flexibility in choosing an expansion around a certain row or a certain column instead of being stuck just in the top row. And then once we've got this, we'll leverage it to demonstrate a simple formula for the determinant of a triangular matrix, one where almost half the entries are zeros. The entries either all below the diagonal are all zeros, or all the entries above the diagonal are zeros. So we'll define that when we get to it. What's interesting here is, in general in mathematics, it's often very fruitful to pay close attention to what you're doing when you do certain computations. We've already seen this with, say, the row reduction algorithm, where by abstracting that it's really just three operations that we need to row reduce the matrix to its row reduced echelon form, and analyzing that those can actually be thought of as multiplying by elementary matrices, we're able to understand things much more deeply than if we were just kind of trying to solve the equation and doing it a little bit more haphazardly. So it's nice to have theorems that tell us that we can do computations in more general ways. And so here, let's take a look at the definition. So for a matrix, which I'm going to call, the entries are going to be little a sub ij. So I've got A11 in the upper left-hand corner, and going down the diagonal, it's A22, A33. Going across the top row, it's A11, A12, and so on. I'm going to define capital A sub KL. It may not be what you would initially think at first. This is actually going to be the matrix which has everything except row K and column L. Okay, so it'll be the n-1 by n-1 matrix because I've eliminated one row and one column. And let me just show you quickly what that looks like on an example. This is sometimes called the minor of a matrix. So capital A11 here is going to be delete the first row, delete the first column, and what are you left with? You're just left with 1, 4, 2, 3, a 2 by 2 matrix. Okay? On the other hand, if it could be a little more complicated, they're not always necessarily contiguous. So I could have something like A23, capital A23 here would be, okay, I delete the middle row, 2, and I delete the third column, right? So I delete this column and this row, and so then what I'm left with is 1, 2, negative 1, 2. That's going to be the matrix that I'm left with. So this guy is this is called the minor of a matrix, and it's the k-lth minor, okay, where I delete the kth row and the lth column. Now I'm going to define the determinant inductively. So first I need to tell you, if I have a 1 by 1 matrix, what do I get? For a 1 by 1 matrix, the determinant of A is just that single entry. What else could it be, right? And for k bigger than or equal to 2, it's going to be the following thing. There are two different notations for determinant. There's the absolute value notation for the determinant, or there's det A. In either case, what the determinant is going to do is input an n by n matrix and spit out a single number, which will give us some information about the matrix. And the way you define that number is you take A11, so that's this entry, little a11, and you multiply it by the determinant of capital A11. So that's the determinant of 1, 4, 2, 3. And then you subtract this entry times the determinant of what you get when you delete the top row in this column, so 0, 4, negative 1, 3. And then you add it to 3 times what you get when you delete that row and the third column. So let me write that out explicitly for you so you can see what's going on. So by definition, this should be equal to what? It should be equal to 1, that A11 entry, times, I'll write the determinant just like this because it's a little bit cleaner, the determinant of the matrix where I delete this row and the first column, so it's 1, 4, 2, 3. Okay? And now I subtract 2, because I'm expanding across this top row, 2 times what I get when I delete that row and the second column, so 0, 4, negative 1, 3. And then I add back 3 times the determinant of what I get when I delete that first row and this one, so 0, 1, negative 1, 2. 0, 1, negative 1, 2. Okay? So does that make sense? All right, and so that's what this definition is saying. So I just go plus, minus, dot, dot, dot. The last one will be negative 1 to the 1 plus n. That's just the right sign, times. So the coefficients in front of these other determinants are just the values across the row, a11, a12, dot, 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 a1n. And it's the corresponding minors, the determinants of those minors, that give me these values. OK, so what is this equal to? Well, it looks like it's going to be equal to, so this determinant, well, remember for 2 by 2 determinants, it's just AD minus BC. We'll see why that's true in a second. So this is just 1 times 3 minus 8. So 3 minus 8 is negative 5, right? So this is negative 5. Now minus 2 times, what do I get? 0 times 3 minus negative 1 times 4. So minus minus 4 is plus 4. So it's going to be minus 2 times 4. And then the last one is going to be 3 times, well, 0 times 2 is 0, minus negative 1 is plus 1. So plus 3. And when everything settles, what is that? That's negative 5 minus 8 plus 3 should be negative 10. OK? So that's the determinant of this 3 by 3 matrix. I started with a 3 by 3 matrix. And my final answer, the determinant of this, is just the value negative 10. OK. Now, we'll talk more about other ways to compute this and what this means. But first, I want to show you that there's a very important generalization of this definition, not immediately obvious. But I need a definition, which is that I'm going to define, it's a little inconvenient to write out det of aij all the time. So I'm going to define the ij cofactor to be this thing. Cij is equal to, it's the sign, negative 1 to the I plus j. So that's actually the same sign that I was getting here, times the determinant of aij. OK? So I just delete the ith row, the kth column. I'm left with an n minus 1 by n minus 1 matrix. I multiply it by a sign. Those are the things that I'm going to add up, weighted by an appropriate row or column. And so here's the amazing theorem, which we don't really have the best tools for tackling this. It would just be a very computational proof, so it's not worth getting into. It would take us too far afield. But the determinant of A is, well, I can either pick row k, and I can say, OK, along row k, I have ak1 times that cofactor, ck1, plus dot, 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 plus akn times ckn, that cofactor at kn. Right, so this is all going across a row. Or I can go by a column. Right, when I fix this A1L, A2L, and so on, I fix L, that's fixing a column of the matrix. And I can say, well, it's A1L times that cofactor plus dot, 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 plus ANL times that cofactor. So the upshot is that we can compute the determinant of A by expanding along any row or any column, whichever one we feel is most convenient. And so let me show you that right here. First of all, let me show you, how do you get this sign? The way this sign works is, well, 1 plus 1 is 2, so the sign should be positive at A11. So if I'm thinking about my matrix as being, I've got, A11, A12, A13, A21, A22, A23, A31, A32, A33, something like that, then the cofactor matrix of signs is going to be plus here, because 1 plus 1 is 2. And then anytime I move over or down, I'm just changing the sign, right? Because I'm increasing one index by 1. So I'll be plus, minus, plus, minus, plus, minus, plus, minus, plus. If it were 3 by 3, but you can just keep going, dot, 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 and keep going down, right? So if I have any n by n matrix, it always just goes plus, minus, across, down, and then that tells you it's always alternating in every row and column. Okay, so that's what this sign, c minus 1 to the I plus j, is really telling you. All right, so now let's see what would happen if we tried to redo this computation using a different row or column. So let's say instead that we want to expand, instead of expanding along the top row like we just did, let's expand along this column. What will we get? Well, if we expand along this column, then we get 1 times now we need the determinant of, we eliminated this column, we eliminate that row, we get 1, 4, 2, 3. Now we have 0 times the next one, which would be 2, 3, 2, 3, but it doesn't matter, right? Because it's just plus 0 times, who cares, right? And now we're going to have, it would have been negative 0 though, right? Because it has to alter, it would have to be this sign. And now it's going to be positive times negative 1 times what? Times the 2, 3, 1, 4. Okay? So this 1 and this minus 1 are actually not the sign and the cofactor. These are the aij's. Okay, so what do we get? If we get 1 times this, we get 1 times 3 minus 4. So this is negative 5 again. Here we get 0. And then the last term, we get 8 minus 3 times negative 1 minus 5. And that's equal to negative 10 again. So the point is, it doesn't matter how you do it, right? If I do it by this 3, 4, 3 method, just to show you one more way, right? So if I go down this column, this isn't as some people make better choices in life than others. And, I would say that the best choice in this case is either to do it down this column or across the middle row, because then you have the 0 and it saves you some computation. But if you weren't thinking that and you just wanted to see, this is amazing that all these computations turn out to be the same, which it really is in a way. Let's see what would happen if, let me take a different color. What would happen if we expanded instead along the 3, 4, 3 column? So now we're over here, and we would have what? Well, it would be 3 times the determinant. When I eliminate that column and that row, it's 0, 1, negative 1, 2, plus 4 times, oh wait, and so plus minus plus. So this one is a plus. And now it's going to be plus 4 times minus 1, right? Because this should be a negative sign here. And it's negative 1 times 1, 2, negative 1, 2. Okay? And then the last one is positive 3 times 1, 2, 0, 1. Right? And the reason I'm writing it all out this way is so that you can just see the cofactors more clearly, right? So the cofactor, the 3, 4, 3 are the entries, and then this cofactor incorporates that sign as well as the determinant. So now if we just finish working this out, what do we get? So we end up with negative 3 times, that's a 0, and that's a minus minus 1, that's a 1. So this looks like we get negative 3. And now here we're going to get plus 4 times negative 1 times, okay, what do we get? 2 minus minus 2 is 4. So it looks like we get 4 times minus 1 times 4. So that's negative 16. Uh-oh. Why would we get the same answer? The computation looks completely different. All right, so now what do we get here? Plus 3 times 1 minus 0. Okay, so what do I get? Looks like I get negative 16 minus 3 plus 3. So now I'm looking unhappy because it looked like I didn't get negative 10. So can I quickly find my mistake, or can you find it before I do? So let's see, what did I do? I expanded on this column. This should have a plus sign, a minus sign, and a plus sign. So I got the, so why did I have a minus here? Ah, that's the problem. There shouldn't be a minus 1 here at all. So then this becomes a plus 3. And there we go. So now I have 3 times, again, this was a positive 1, plus 4 times negative 1 times 4. So this is 3 plus negative 16 plus 3. And that turns out to be exactly negative 10 again. Okay? So very useful that you can do this either way. And we'll see how to apply this again in the next slide. Okay, so before I talk about triangular matrices, there's one thing that I forgot to say earlier, which is, why does this definition make sense for 2 by 2 matrices, right? So we know in general that the determinant, what should be the determinant by this of A11, A12, A21, A22, right? So this is what this would look like. Well, if I expand it, say, across the top row, right, then this should be equal to, well, it should be equal to A11 times, when I blot out this row and this column, I'm just left with A22, right? And now when I add this term, then I get plus A12. When I get rid of this, the remaining cofactor is just A21, except that it's a minus sign because this is a plus and this is a minus. So it's a minus A12 times A21. And that's just the familiar AD minus BC formula that we have from before. Okay, so this is a minus sign, and it's the same thing. Okay, so that it agrees with what we said before, as long as we define a 1-by-1 matrix to have determinant just that equal to that value. All right, so now let's look at another example and think, you know, if we're a computer and we can't really, you know, nobody programs us right, we might just say, well, definition of determinant. It's going to be 2 times this 3-by-3 matrix plus 4 times that 3-by-3 determinant plus 1 plus, or, you know, minus 4 times that 3-by-3 determinant plus 1 times another 3-by-3 determinant minus 3 times a fourth 3-by-3 determinant. Right? And then each of those 3-by-3 determinants you would expand into 2-by-2 determinants inductively. But if you're clever about it, then you can do much better than this, right? So how should we expand the matrix like this? Well, you know, pretty clearly we'd rather do it, we want to have the maximum number of zeros possible, right? So we either want to expand along the first column or along the bottom row. And either way you do it, we'll see that things work out nicely. Let me just do columns so that you remember that you can do it around any row or column. So if I expand around this column, what am I going to get? Well, it's really nice, right? Because what happens is that I get 2 times, let me make sure I leave space. So I'm going to get 2 times the 3-by-3 determinant, where I eliminate that column in that top row. So I just get 2 times 3, -1, -2, 0, -2, 3, and then 0, 0, 1. Okay? Plus 0 times something plus 0 times something plus 0 times something, which I don't need to worry about, right? Okay, so that's great. And now what do I do? Well, you know, look, I still have a bunch of zeros here, right? So I've got 2, and now I can just expand this as 3 times this 2-by-2 determinant, right? So this is going to be equal to 2 times 3. Now notice, right, this 3 has a positive sign because it's the upper left. It doesn't matter that over here it might have been different, although it turns out to be the same. Well, the only thing that matters is now that it's a 3-by-3 determinant, where it is in that place. So then we'll have 2 times 3 times, we'll get a 2-by-2 determinant here of -2, 3, 0, 1. Now we could just use the formula for the 2-by-2 determinant at this point, but look, this is exactly the same form again, where we have, you know, if we expand along this column, we'd have -2 times 1 and then plus 0, right? So this is equal to 2 times 3 times -2 times 1. And when you look back at the original matrix, you see, okay, what did I do? I actually was just multiplying those diagonal entries, right? Because these zeros killed off all the other terms that I might have to worry about. And so this is something that happens in general, and it's really nice. So we'll call a matrix A equals AIG upper triangular if AIJ is equal to 0 whenever I is bigger than j. So what does that mean? Let's look at this example. This is an upper triangular matrix. And what this condition is saying is that I can have non-zero things on the diagonal. But as soon as I get below the diagonal, as soon as my row index is bigger than my column index, I greater than j, things have to be 0. And you can see I have this whole nice triangular pattern of zeros in this matrix. So let's see if I can draw this so you can see it. So here, 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 right? That's the triangle we're talking about. On the other hand, if instead of having my triangle of zeros here, I had it on the upper right part, then I would call it, that a lower triangular matrix because all the action is happening in the lower part. So upper triangular means everything interesting is happening in the upper triangular part, and the rest have to be zeros. And lower triangular is the other way around. That corresponds algebraically to saying that aij equals 0 for I less than j. In other words, the row, you're in this chunk of the matrix if your row index is less than your column matrix. Either way, we'll call A a triangular matrix. So we have two different kinds of triangular matrices, upper triangular and lower triangular. We don't deal with triangles the other way, so it's just these two different kinds of ones that come up all the time. All right, and so here's the theorem, which we've just seen illustrated. Really, this is basically the proof. If you have a triangular matrix, then its determinant is just the product of its diagonal entries. It's just A11, A22, ANN. Okay? And the reason is exactly what happens here. You can expand it in such a way that you only have one non-zero entry in each successive Laplace expansion. So just to do another quick example, if you had something that was lower triangular, what would happen? So let's see, suppose we have a matrix like this. So we could have anything here, but then we've got 1, then we have to have these 3 be zeros, and then we could have anything we want here, and then maybe this is a 2, and then this is 0, 0, and then we can have anything we want here, anything we want here, and we can really have anything we want on the diagonal as well, but that has to be 0. Right? But suppose we had a matrix that looks something like this. Then what would happen when you try to expand it? Well, now what you want to do is expand it this way, right? And so you'll just get 1 times this matrix. And now when you expand this matrix, you'll just say, OK, well, this is just 2 times this matrix. OK, and then finally, the last step, you'll just have 3 times this matrix. And that's just one entry. So 1, 2, 3, 4. So you just have the product of those diagonal entries. OK, so that's the first theorem in determinants. And in upcoming lectures, we'll see more things about how properties that we can use, more abstract properties of these things that will help us understand matrices more deeply. There's one other point I should note numerically, which is that actually using any of these kinds of expansions to compute determinants is unhealthy. It uses a lot of computer time. So for those of you who know a little bit about how computer running time, if you're going to try to compute using this way, you're going to end up doing something like, in general, order of n factorial, not in the triangular case, but in the general case, you'll have something like the big O of n factorial different multiplications you'll have to do. So even for like a 30 by 30 matrix, you don't have the computer power to do it, even with really fast computers these days. Take you thousands of years. But you can do it much more efficiently. So we'll actually see that row reduction again comes to our rescue, and there's an algorithm using row reduction that allows us to compute the determinant in something like in polynomial time, something like the order of n cubed. And so that's a much easier, that's a much better way for actually doing the computations. Let's see, is there anything else I needed to say? Oh, I didn't even tell you to compute this for you. This is -12, of course. But you didn't need me to tell you that. And I guess upper triangular and lower triangular matrices in general, I would say, well, so an upper triangular matrix has the form star, 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 0, star, star, where star means it can be anything. Right, so that's lower triangular. And then upper triangular would have the form star 0, 0, 0, 0, no, sorry, star, star, 0, 0, star, 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 0, where this is kind of regular expression language for saying that the stars can be any values you want, but the zeros have to go where I put them. 3, 2, oh, this doesn't have to be a 0. Right, so in each one there's 3, 2, there should be 6 zeros in each one. Good. Okay, that's it for the introduction to determinants. Thank you for your kind attention.